Hello students, this is Sanjana from Computer Science Department. In this class, we are going to discuss about don't care conditions in K-maps and MC-Klasky method. Now let's get into our topic. See here, now let's get a look into about this don't care conditions in K-maps. See, it is one of the significant and useful concept in simplifying. Whenever the output of the expression, see, whenever you are going to solve the K-map, what are the output that we are going to get, then it is a concept called don't care. Here it allows us to replace the empty cell of the K-map to form a grouping of the variables. Suppose in a K-map we are having some cells, we are also having 2 variable K-map, 3 variable K-map, 4 variable K-map. We have already seen that. Suppose in that K-map if you are having some empty cell, if you in order to get some expression, if you want to replace a variable, then it will be a some there we have to use some condition called this don't care condition. Then this don't care condition will come in, will get into this picture. But here the basic thing is it allows the don't care condition. It simply allows us to replace. See, if we are in 4 variable care map, we are having simply 4 by 4, that is 16 cells. If it is having any empty cell, then it in the don't care cell and don't care condition, the basic thing is it allows it is allowing us to replace the empty cell of a K map to form the grouping of the variables. In order to form the grouping of the variables, we have to replace that one. Then which is the larger than that forming the groups without don't cares. Without don't cares, we are not having whether which is the larger one and which is the longer one. We don't know how to group that cells. And next one is while forming the group of the cells, we can consider we can't able to consider don't care. Suppose if it is a cell 1 or cell 0, we cannot able to ignore that cell, because therefore a don't care condition can help us to form a large group of cells. See here in this in this don't care condition, it is larger than that forming the groups. But without don't cares, while forming the group cells, we can consider a don't care cells. Whether it is a first cell or zero cell, we can simply ignore that cells. By simply ignoring that cells, we can say that it can form as a large group of cells. By using that large group of cells, we can get into a condition just like that. But if it is not a significant thing, some of the but by using this, we can say that it can be the useful concept for just for simplifying the output expression of the K map, but it is not a concept of that basic thing. Here it is in this the condition, the basic condition is it is allowing us to replace the empty cell of the K map to form a grouping of the variables. In order to form the grouping of the variables, we are going to perform the these K map cells. But here therefore from this we can say that don't care cell as 1 or 0, we can also ignore that cell here. And next one is therefore the don't care condition can help us to form a larger group of cells. See here basically the main thing in the don't care condition is it is very basic thing, and it is useful concept in simplifying the output expression using the K map. See here don't care cell can be represented by a cross mark. See, if it is not having any variable in that particular cell, then it will be indicated by the cross mark in that K maps. Suppose if it is not a valid combination, suppose if it is an invalid combination, Suppose if you have observed something in an example, for example in the XS3 code system, suppose we have already done with some codes, binary code, decimal code, just like that. XS3 means you have to add the three more digits to that number. Suppose if it is 1001, if you have if it have done 3, then it will becomes the 0 will becomes 3, just like that. Suppose in that XS3 code system, the states of 00, suppose it is a 0 1 2 4 7 8 16, just like that. If it is unvalid or unspecified, we can say these are called as don't cares. If it is not unspecified, unspecified means if they have not specified till the end, here, and it is converted into a POS expression by simply keeping the don't cares as they are writing the missing min terms of the sum of the products to form the sum of the products as a max term of the product of the sum. Similarly, from that the product of the sum function, we are not taking this condition as that, but by having keeping something just like that. So by writing this missing min terms of the sum of the product as the max term of the product of the sum, similarly as the product of sum function having don't cares can be converted to the sum of the product from keeping the don't cares as they are writing and missing max terms of the POS expression as the min terms of the sum of the products. Here, the basically the don't care cell must be represented by using the cross mark. By using the cross mark here, if it is excess core system, these states are like a 0, 1, 10, just like that. If it is not unspecified, then we can say that these are called don't care. So we should not care about those things. But in a standard sum of the products function having don't cares can be these can be converted into a POS expression simply by keeping the don't cares as they were, and they are writing the missing min terms of the sum of the product form and as a max term of the product of the sum form. Similarly, a product of some function having the don't cares, um, simply just like that, simply we can convert them. But maybe an expression also related to that. Suppose if it is a large expression, if it is fully filled by filled this k map, in the K map each and every cell is fully filled, then at that particular point of time it is not be it will not be mentioned particularly. But in the sum of the products and product of sometimes, if it is not an if it is if that cell is empty, simply by keeping the cross mark into that K map, we can represent it as a don't care cell. That is that cell should not be cared for that evaluation of that by a boolean expression. Okay. But a standard sum of the products, or whether it is a sum of the product expression or product of some expression, if we are keeping don't cares, then as a missing terms, then it we can say it as a sum of the max terms or sum of the min terms. We have already said that about the sum of the max terms and the sum of the min terms. But having the don't cares can be converted to the uh, sum of the products from keeping as they are writing the missing max terms of the product of the sum expressions as the min terms of the sum of the product expressions. Okay. Suppose if it is the example, like suppose if you are going to minimize the sum of the products means you have to sum the products. Okay. Then now let us see if this is a function. First one, if we are considering the cells of first cell, fifth cell, sixth one, 11th cell, 12th cell, 13th cell and 14th cell, then we are going to add this DF4. Then see, now let us see the explanation for this particular sum of the product K map for this expression. Now let us see how we are going to solve this particular expression. Simply what we are going to seeing here is simply we are going to solve that how we are going to minimize the sum of the product, how we are going to minimize the sum of the product function by using this K maps. Okay. Now let us see in the Next figure. See, this is first one. This should not be considered. 0 1 0 0 0 0 0 0 0 1 2 0 1 2 3 4 5 6 7. Just like that, we will write now 8 9 8 9 10 11 12 13 14 15. We are having 15 cells here. In which cell, if you observe in the first cell, fifth cell, sixth, 1 5 6 11 12 13 14. 1 5 1 0 1 2 3 4 5. Okay, fifth cell, 6 7, sixth cell, 1 5 6 7 8 9, sorry, 7 8 9 10, 10 cell. Okay, 11th cell, sorry, this one is 0 cell, 0 1, this is second cell and this is third cell, 4 5 6 cell and 7th cell, 8 9 10th cell and this is 11th cell, 12 13 14th cell and this is 15th cell. Okay, here 1 5 6 11 12 13 14, there you have to place the values there. 1 5 6 we have placed, but see 0 1 2 3 here, which one we have to keep as a don't care. See, which cell we have to keep it as a don't care? Fourth cell. Did you observe? See, this is 0th cell. 0 1 2 3 0 1 0 1 2 3 4 5 6th cell and 7th cell. This is 8th cell, 9th cell, this is 10th cell and this is 11th cell. This is 12th cell, this is 13th cell, this is 14th cell and this is 15th cell. Okay, here we have to place first cell, fifth cell, sixth cell, 11th cell, 12th, 13th, 14th cell. These cells we have placed. And next one is, which one is considered as a don't care condition here? This one should be considered as a don't care condition. Then simply we can consider this one as one box, and this one is another box, and this one is one box, and this one is this should not contain any particular combinations. So we are considering this one as a single box here. See, then what are the possible combinations here? If we consider this one as a AB and this one is CD, here we are not having AB here, then so we can simply write it as, first one we can simply write it as, if you are having some possible combination, BC dash plus BD dash plus A dash C dash D plus A B dash CD. See, this is the output, this is the final output that we are going to get here. If you observe, by taking this cell as a don't care cell, we are considering this entire group. By considering this entire group, we will get like this. The final expression that we will get is BC dash plus BD dash plus A dash C dash D plus AB dash CD. This is the final expression that we are going to get in this example of the don't care condition. This is the example that how we are going to minimize the sum of the products form. If this is not the product of sum form, this is sum of the product minimal by using the K-map. Here this is the variables that we are going to place the things, and this one is the don't care cell. By simply solving this particular K-map by using the don't care condition, this is the particular Boolean expression that we are going to get, that is By solving this K map, the expression that we got is BC dash plus BD dash plus A dash C dash D plus AB dash CD. See, now let's have a look into this MC Klasky method. This method is developed in the year 1956. We can simply say this method as a tabulation method. Simply, this method is used for the minimize. Why this method is used means this method is simply used for the minimization of the Boolean function. Only for the minimization of the Boolean functions itself, it is used. See, if we are having the large number of Boolean expressions, it is very hard to build a logic gate. Sir, no. If it is a large Boolean expression, obviously it will become very hard to build a logical. Sorry, it is very hard to build a logic gate. But if you minimize that particular if you minimize that particular Boolean function, then it will be very easy for that particular user to build the logic gate. Here, the Klasky method plays a major role in simplifying the Boolean expression. Suppose if you are using this up to K map, means we have already know that we can say it as a Karnaugh map. Up to 5 bits also we can solve it for up to 5 bits or more than 5 bits also we can solve that Boolean expression there. But here by using the simply we can't say that it is not a basic thing, but it we also has to keep focus to solve that particular Boolean expression. Here it is not an easy and simple task for each and every person to do that, but by using the minimization of the Boolean functions also we can do that. But simply we can say it is not a tabulation, it is not a kind of tabulation method. It is mainly used in the it is mainly used for the minimization. How we are going to minimize the Boolean functions. Okay, it is not a simple tabulation, it is not a simply in the form of tables. It can be mainly used for the minimization, only minimization of the Boolean expressions. But if it is in K maps, we can simply solve up to 5 bits, and more than 5 bits also we can easily solve. But it has a easy algorithm that it can solve for more than 5 bits, but it is not, we can say that it has not that much easy to prove that, and it is such that we can say it is efficient and it can be clearly and easily implemented in the more than it can be used in the computer. Even in the algorithms, how many types of algorithms that we are using also, in that one also we are going to solve that expression. But we can't say that it is not a simple thing just like that. It is in previous years itself it is discussed, somewhere in 1956 itself it is discussed. It is not a some kind of the tabulation method, but it is mainly used for the mainly for the just to minimize the Boolean functions, such that whereas the K map we can solve for more than 5 bits, and it is not an easy kind of algorithm, such that it is an efficient and can be very easily implement for the computer algorithms. Okay, these are the some of the main facts that are related to the MC Klasky method. Okay, go for the next slide. See, these are the four main steps. These are the four main steps that each and every the person who is going to implement uh, this MC Klasky method, that person has to uh, focus on that. These are the four main steps that a person has to that a person has to follow. The four main steps are that person has to generate the person has to generate the first one, it has to generate the prime implicants. Where are the prime numbers? First one, he has to generate the prime implicants for that particular number. And next one is he has to construct the prime implicants for that particular table. He has to generate some table and he has to construct the prime implicants for that particular table. And next one is he has to reduce that prime implicants. And next one is he has to solve the prime implicants table. The main four things that that a person has to follow when he is following that MC-Klasky method is, first one is he has to generate the prime implicants, and next one is he has to construct the prime implicants table, and next one is he has to reduce the prime implicants. He has to reduce the prime implicants, and next one is he has to solve the solve the expressions in the prime implicants table. Okay, go for the next slide. See, look at this example for problem. Here we are going to produce the sum of the terms here that we have specified by using the sigma. Sigma means we have to perform the sum of the product operation, and if it is represented with pi, then we have to perform the product of sum operation. In the previous class itself we have discussed. So if you have observed the numbers, that is it is a 4 variable K map that we are going to use there. 4 variable K map means we have to use simply we have to use the 4 variables. So the numbers is 0, 4, 5, 7, 10, 12, 13, 14 and 15. These are the variables. Okay. If you have observed this, the binary codes for each number is, see, this is a step 1. You have to write down the binary codes for each number. See, the binary code for 0 is 0, 0, 0, 0. Why you have used 4 variable? That is a 4 variable K map. No, that's why we have used up to 15 it has given. So up to 15 means it is a 4 variable K map. So we have to write the binary code for each and every. 0 means 0, 0, 0, 0. 4 means 0, 1, 0, 0. Next one, 5. The binary representation of the 5 is 0, 1 and 0, 1. Next one, 7. The binary representation of the 7 is 0, 111. Next one is 10. The binary representation of 10 is 1010. Next one is 12. The binary representation of 12 is 1100. Next one is 13. The binary representation of 13 is 1101. Next one is 14. The binary representation of this number is 1110. Next one. The binary representation of 15 is 1111. Here in the first step you have to list the binary code for the each and every number. Okay. Go for the next slide. See, what is the step 2? After listing the binary numbers, we have to take the binary numbers according to the number of ones as in the table. See how many number of ones are there here. We have to take into the list. Then the making the table of duals from the table 2. See, from this table you have to do the dual operation here. See, if it is 0, you have to take it as 0.04. Okay, next one is 4.5. Next one is 4.12. Next one is 4.7. Next one 4.5, 4.12. Next one is 5.7, 5.13. Just like that, we are going to make the table of jewels from this table too. See, if you have observed this table, this is 0, 0, 0, 0, 0 to 4, 4 to 5, 4 to 12, up to here completed. Next one is 5 to 7, 5, 13, 10, 14. Next one 12 to 13, 12.14, 7, 1, 5, 13, 1, 5, 14, 1, 5. Just like that, we have represented it in the. We are going to make the table of jewels from the table 2. Here in this step 2, we are going to list the what are the binary numbers according to the table 1, that we are going to list the, and according to the number of ones in the table we are going to replace that one. Okay, based upon the number of ones in the table we are going to replace that variable. Based upon this, we have taken this, and from this we have applied the step 3. After applying the step 3, this is the resultant table that we are going to get here. See, of this one we are considered as it is a uh, we are going to generate the table of quads from the table 3. See, quad means up to 4 we are going to take. So from this we are going to take this table of quads. Just like that, it is considered as a parity instruction, and just like that we are going to simply move on into the case. Okay, see, this is how we are going to generate 0, 4. This is 10th place, and this is 1.14. This is 4th one, 5th one. This is 12th, 13th bit, and this is 5th one. This is 13th one, 5, 1, 3, 7 and 1, 5. Next one 12 and 13 and up to 14 and 15. This is how we are going to add the sum of the products. Sum of the products 0 into means sum of the products are 0 into 4, 10 into 14, 5 into 13, 7 into 15. Just like that we are going to perform the multiplication operation first, and after multiplying that we are going to add those variables. See, after adding that, this is the minimized sum of the product expression that we will get. See, this is the final step. We have to generate the sum of the products from the prime implicants, that is 0, 0, 4, 10, 4, 1, 4. Just like by simply by this we are going to perform the boolean expression. We are getting the boolean expression here. This is about how we are going to see. This is about the don't care conditions and the simplification. This is about the don't care conditions and the simplifications, how we are going to perform, and about the MC class key method. In next class we will continue the next topic. We will continue with the next topic. Okay.